Welcome to this video that's going to talk through everything you need to know for GCSE Physics Paper 2. It's suitable for separate and combined science students. I'll point out the stuff that's separate science only. Let's start off with forces. Forces can be split up into two general types, contact and non-contact. Contact forces include friction, air resistance and tension, so when you pull something tight, normal force or reaction force, and the non-contact forces would be gravitational, electrostatic and magnetic force. How you define a non-contact force is to say it doesn't need to touch an object for force to be exerted. Like in magnetic forces, when you put a north and a south pole close to each other, they don't need to touch to be able to attract each other. Forces are an example of a vector quantity. Vectors have both a magnitude or a size and a direction, whereas scalar quantities have a magnitude or size only and no direction. Here are some examples below of scalars and vector quantities we need to know. When we are describing the resultant force acting on an object, and that's measured in newtons, what we are describing is basically the overall force. So in this case, if I've got 3 newtons acting to the left, but 10 newtons acting to the right, we subtract those two because they're acting in opposite directions, giving us overall 7 newtons acting to the right as our resultant force. If we've got this situation down here, where we've got 10 newtons acting to the left, but 3 newtons also acting in the same direction, we would add them together. So the resultant force is going to be 10 plus 3 makes 13 newtons, this time going left. To define resultant force in words, we would say a single force that has the same effect as all the forces acting together on an object. We can also use free body diagrams to determine resultant forces. So in this example here, I've got 7 newtons up and 7 newtons down, 3 newtons left, 10 newtons right. Now the idea behind a free body diagram is it just simplifies the forces acting on an object. So this object here could be a plane, it could be a car, or whatever. I've just represented it as a simple circle to show what it is. And that it means it's a free body diagram because body is the fancy physics word for an object. Now, if you're studying higher tier, you need to know this next bit, which is how to work out resultant forces if they're not in the same plane, i.e. they're not both vertical or not both horizontal. So in this example here, I've got a 300 Newton force acting upwards and a 400 Newtons acting to the right. So how do I work out the resultant force? Hopefully it's obvious that the force is going to be going sort of up and right diagonally, but how can I work out its magnitude and its direction exactly? What we need to do is to draw this diagram to scale. So if I've drawn this diagram to scale, I've got 3 centimeters going up and 4 centimeters going across. Then what I do is I complete the rectangle to make it into a rectangular shape, and I draw the resultant force from, in this case, the bottom left to the top right, going across from one side to another. Now you can see diagrams asking you to draw it tip to tail. This is an equally valid method, and I think makes a bit more sense when you're drawing it. Now when you've drawn that arrow in, you then measure the length of the arrow, so in this case it's 5 centimeters long, and you convert back to your scale. So in my scale I've got 1 centimeter is 100 newtons, therefore 5 centimeters gives me 500 newtons. Now you could have the most difficult question you could have about this topic is not a rectangle, but if you've got the two forces that aren't perpendicular to each other, they're slightly a different angle. In this case what you do is instead of completing the rectangle, you'd make the shape into a parallelogram, but everything else is the same. Your resultant force would be from the bottom left to the top right, and you'd find the length of it, convert it back into whatever units you're using your scale. The opposite of this process is called resolving components or resolution of components. And because it's the opposite of this process, what it means is that you have given to you initially a resultant force and you've got to sort of split it up into its component forces. These component forces have got to be at right angles to each other, and then the X and the Y, or the vertical and the horizontal directions. So how we do it is, first of all, we'd be able to measure our initial resultant force, and then we'd sort of do the reverse process of making it into a rectangle and measure the length of the sides of those rectangles. So here, using the same example as before, I've got my Y force going vertically is 3 centimeters, meaning it's 300 newtons, and my X force, or going horizontally, is going to be 4 centimeters, so 400 newtons. So I've split or resolved my resultant force into 2 equal components, into two perpendicular components. Let's talk next about Newton's law. So Newton's first law says an object will remain at rest or at a constant speed unless a resultant force acts on it. So if a car isn't moving, it's going to stay stationary unless there is a resultant force, unless someone puts their foot on the accelerator. However, if it is already moving and it's got balanced forces, so 100 newtons forward, 100 newtons backwards, the resultant force is 0, it's not at rest, it's going to carry on going at a constant speed because it's already moving. It doesn't suddenly slow down, just carries on in uniform motion, would be the other way of putting that. Newton's second law is to do with force and acceleration. It states that force is directly proportional to acceleration, and acceleration is inversely proportional to the mass acting on the mass of an object. Putting those two things together, we get the equation F force equals m mass times a acceleration, and I've given you units there as newtons, kilograms, and meters per second squared. If you're studying higher tier for combined science or separate science, you need to know about inertia or inertial mass. So inertial mass is a measure of how difficult it is to change the velocity of an object, and it's given by the force divided by the acceleration, basically rearranging Newton's second law. If you're asked about inertia, so not inertial mass but just inertia, it is said to be the tendency of an object to remain at rest or at a constant speed. Newton's third law is one of the most famous ones out of the three, says that when two objects interact, the forces they exert on each other are equal and opposite. So an example of that is you sitting in your chair right now, you've got weight acting downwards. Let's say it's got the exact opposite direction, normal force acting upwards, 100 newtons down, 100 newtons up. That means the resultant force is 0, and as an example of Newton's third law, because the force that's acting upwards on you is equal but in the opposite direction of your weight. So the weight of an object is different to an object's mass. Weight depends on an object's mass, but also on gravitational field strength. So gravitational field strength varies depending on the planet, but weight is directly proportional to an object's mass. And the equation to calculate weight is that weight is equal to the mass of an object times by the gravitational field strength, which is 9.8 on Earth, but you could be given a question about a different planet or a different situation. But important to note that it's different to mass. Mass is the amount of matter in an object. Weight is a force, as indicated by the units in this equation, it being in newtons. Next, let's talk about centre of mass of an object. So centre of mass of an object is defined as the point where the mass of an object can be thought to be concentrated. Note that it's not actually concentrated there, it's just where we can consider it to be concentrated. And it always hangs below point of suspension. If it's suspended from a point, like a person on a swing, the person's mass is always going to come to rest below the point where it's suspended from. Hooke's law says that the force applied to an object is directly proportional to its extension, only up to the limit of proportionality. So an example of an elastic object would be a spring. If I apply force by varying the masses added to an object, I'm increasing the weight, or a force going downwards, it's going to extend. If I was to plot a graph of the force in the extension, the bit where it follows a straight line would be the part where it follows Hooke's law. The bit where it curves upwards would be where Hooke's law is not followed, so therefore that's our limit of proportionality. Now Hooke's law also applies to compressing objects, not just extending objects. Where we talk about extension, we are just going to make the negative of that, compressing it. The same thing applies, like for springs in an object like a bed or a sofa or something. The equation to do with Hooke's law states that force is equal to a spring constant, K, multiplied by an extension. Now, force is proportional to extension. The spring constant is just a number, a value that's different for each spring or each object that determines their relationship of proportionality. It's given in newtons per meters because force is in newtons and extension has to be in meters. You can calculate it from a graph by using the overall force divided by the extension, which could be the gradient or could be the inverse of a gradient. When you stretch objects that are elastic, you are storing elastic potential energy. So the elastic potential energy stored is given by half times by the spring constant times by the extension squared, just like it is in paper 1 when you talk about energy stores in different forms. Elastic objects we define as ones that can return to their original shape, and inelastic objects is the term given to objects that do not return to their original shape once deformed, like Play-Doh or blue tack or something like that. Once stretched, it stays stretched. The next part of this video is going to be suitable only if you're studying separate science only. The moment of a force is described as the turning effect of a force. So for example, anything that turns, when you exert a force to it, you're exerting a moment. So like a door handle, you've got a pivot, the point at which the object rotates about. If you exert a force downwards on the door handle, the thing will turn. It doesn't all move, but it'll turn about the pivot. That's described as a moment. The moment can be calculated by multiplying the force times by the perpendicular distance from the line of action to the pivot. That's given by D on your equation sheet, but it's important to know D is perpendicular distance from the line of action to the pivot. Now, if I was to make the distance of the door handle larger, a larger distance would mean I've got a same moment I can apply. That means I will actually need a lower force. So the moment to open the door wouldn't change, but because I've got a larger distance, a larger door handle, I would need a lower force. So make sure you can use this equation to explain different things in different situations. When objects are in equilibrium, it's said that the moments acting clockwise must be equal to the moments acting anti-clockwise, or the sum of the moments acting clockwise equals the sum of the moments acting anti-clockwise. Equilibrium is the fancy word for balanced, and we can use a seesaw to demonstrate this. So if I've got a pivot in the middle and I've got people on either side of the pivot, it means that the total moments acting going either way would have to be equal for the seesaw to remain in equilibrium. So in general, if I'm going to just reduce it to one person per side on the seesaw, I can use this principle to make calculations about the distances or the forces of the people. So considering going clockwise and anti-clockwise, if I know the force of person 1 times by the distance they are from the pivot, then that has to equal the force of person 2 multiplied by the distance they are from the pivot. Putting numbers into this, if I say the weight of the person 1 is 10 newtons, multiplied by distance of person 1 is going to equal the weight of person 2, 20 times by 3 meters in this case. If I was to find out what distance that person 1 has to be away from the pivot to make it balanced, I would put these three numbers into my little equation here, and I'd solve for D. In this case, it would give me 60 on the right hand side divided by 10 on the left to give me 6 meters in total, which makes sense because it's double the distance that person 2 is away, and they've got half the weight. Something else you need to know about if you're doing separate science is what gears are. The main purpose of gears is to transmit rotational effect of forces. Transmit means to sort of pass on, rotational means things that are turning. So in this example of a bike or a bike chain, we've got the bike chain is responsible for transmitting the force from the pedal, the person pushing down on the pedal, to the gear on the other side, which also rotates. So there's been a forces being transmitted, or rotational forces being transmitted. Gears can be connected together like we see here. So if I was to rotate the initial gear, the one with red, in an anti-clockwise direction, in a clockwise direction, the one next to it rotates in the opposite way, in an anti-clockwise direction. Now, for them to travel at different speeds, that's because they would exert the same moment on each other, but because gears have to be different sizes, and that's the whole point of them, they're going to have different diameters. Because they have different diameters, that means they have different distances, which, as we discussed earlier, means the force will be different on each one. That's why they can turn at different speeds and different rates, and apply different forces to a bike, for example, when going uphill. Something else you need to know for separate science is what pressure is. So pressure, we might remember, comes up a little bit in paper 1 when we talk about gas pressure, is defined by the force per unit area exerted perpendicular or normal to a surface. This is given by the equation P pressure equals F force divided by A area. Force is in newtons, area has to be in meters squared, so pressure can have the units newtons per meter squared, or alternatively pascals. It's the same thing, both equivalent units. If you were to look at skis or snowshoes or something like that, the reason why they're less likely to fall through the snow compared to people's feet is that they have an increase in area. Because area is on the bottom of the fraction, we say it's inversely proportional to pressure, so increase in area means that pressure goes down, which means they're less likely to fall through the snow. Pressure in a fluid is equal to the density multiplied by gravitational field strength multiplied by the height it is below the surface. So let's take a submarine, for example, right beneath the surface of the ocean. Its h height beneath the surface. As it goes deeper and deeper, h increases. That means the pressure also increases. Now the reason for that is because there's a greater mass of water above it, meaning there's a greater weight of water above it as well. Now weight is a force, therefore means there is a greater pressure. Using this knowledge also helps us explain something like upthrust. So upthrust can be explained because an object submerged in water or on the surface of water will have a greater pressure below it than there is above it. Because there's a greater pressure below it, that means there's a greater force below it than there is above it. So there's a resultant force pushing it sort of back up, which is described as upthrust. We can use this idea when we're talking about gases as well. So this applies for liquids, it also applies for gases. Around the Earth, we've got an atmosphere, which is obviously made up of lots of different gases. If we stand on the surface of the Earth, even though we can't see it, there are air particles all around us exerting what's called atmospheric pressure on us. The pressure is greater near the surface of the Earth and lower the further away from the surface of the Earth. This is because, just like in the water, we've got more particles, this time air molecules, above us. So therefore, the closer you are to the surface of the Earth, the more weight there is above you. So therefore, the greater the pressure is. If you go up some mountains like Mount Everest, the pressure will decrease because there's less air above you, so there's less weight. The air density will also decrease, which is why lots of people find it difficult to breathe up very tall mountains. Now, all this pressure in a gas is caused by air molecules or air particles. Now, pressure in a gas, we say, is caused by particles colliding with a container wall. When they collide with the container wall, they bounce off, exerting a force on that specific area. Now, we know that pressure equals force over area, so therefore pressure is exerted if there is a force exerted, because pressure is proportional to force. Let's talk about the motion side of this topic. Let's talk about speed and velocity first of all. As we mentioned earlier, speed is an example of a scalar quantity and velocity is a vector. That's because speed doesn't need a direction, whereas velocity is always described with a direction. To calculate the distance or the speed, you need to use this equation here. Distance equals speed multiplied by time, with distance in meters, speed in meters per second, and time in seconds. Now, while this equation is correct, if I was to know the displacement of an object, that would tell me the velocity. So if I wanted to work out the velocity of an object, instead of distance over time, I would do displacement over time. So to look at what the difference is between displacement and distance, I'm going to draw a quick diagram for you. So let's say this is someone's journey, perhaps home from school or to wherever they're going. They're going to cover a different amount of distance because they're going to be changing direction, going left, right, and eventually they'll end up at point B. Now, the distance traveled is indicated by red. If I was to work out the displacement, that would be the straight line distance from A to B. So if I could just go in a straight line with a direction included, so there must be an arrow on it. In this case, it's roughly about southeast, but you could work it out with a protractor. So that's what displacement is. That's why it's described as having a direction. Now, one part of the AQA specification, you need to know the typical values for someone walking, running, and cycling. So for walking, someone's going to be traveling at roughly 1.5 meters per second. For running, traveling at roughly 3 meters per second, and cycling would be about double that, 6 meters per second. Obviously, these numbers are all approximate, but it gives you a general idea if you calculate something, whether you're in the right range or not. For objects traveling in a circle, even though they might be traveling at a constant speed, their velocity can be changing. That's because, as we discussed, velocity is a vector, so if velocity is changing, that means that direction must be changing if it's traveling at a constant speed. If velocity is changing, then that means it must be accelerating towards the center, which we'll come across in a little bit when we look at what acceleration is. One way of representing distance and speed is by using a distance time graph. So for this journey here, the person or the object is traveling at a constant speed initially because it's a straight line. Then they're going to be stationary because their distance isn't changing, and at the end they're going to be accelerating, getting faster. We can tell this because to work out the speed at any point, we use the gradient of the line, given by the change in y divided by the change in x. So in this case, the constant speed is because the gradient is constant, it's a straight line. There's no gradient for the middle bit, and for the last bit, the gradient will be increasing. If you're asked to find the average speed for a total journey, you need to know the total distance and the total time and divide them, even though the speed might be different at different points. Acceleration is given by the change in velocity divided by time. This little triangle here is delta, it means change in velocity, and acceleration is given in meters per second squared. If I was to represent an acceleration on a velocity time graph, it would look a bit like this. So similar to the last graph, we've got a straight line going upwards. However, this time it doesn't mean constant speed, it means constant acceleration because it's a constant gradient. The horizontal line would be a constant speed, and the only time we can consider the object to have stopped is if the line goes back down to the x-axis, meaning it's stationary, it's got zero velocity. At any point, the gradient would give us the acceleration of the line. So it's a constant acceleration if it's a straight line. If it was curving, it'd be a non-constant acceleration, and it's not got a gradient for the horizontal part, therefore it's going at a constant speed. To work out the distance travelled, we need to know the area under the graph. So the area under this graph, if you split it up into different shapes, you've got a triangle initially, then you've got a red sort of rectangle, then I could split it into another triangle at the end. So I need to know how to work out the area of a triangle, half base times height, then the area of the rectangle, then the area of the triangle at the end. One of the trickiest examples you can get, which is only if you're doing Hyatt here, is what if it wasn't a straight line? What if it was a curved graph? In that case, what you'd do is you'd have to estimate it, and questions will always say estimate it. You'd have to count the squares underneath the graph. Now, if you count the squares, you need to know what each square represents. So you work out what each square represents using the axes and count the number of squares, estimate the half squares or quarter squares as well. Normally there's a range with these kinds of exam questions. The final equation you could be asked to use, which is purely just an application question, is if you're asked to work out velocity and you have the acceleration and the distance. So this equation is that the final velocity v squared minus the initial velocity u squared is equal to 2 times the acceleration times the distance. So this is just an application question. Check out my other videos on difficult exam questions if you want to find me walk through one of these calculations. They can be quite tricky. Next, let's talk about terminal velocity, so linking the ideas of forces and motion together. So terminal velocity can be lots of examples. We'll go through one which is a parachutist or a skydiver jumping out of a plane. So initially, just the instant they jump out of the plane, so time is 0, the weight causes the person to accelerate, so therefore their velocity is increasing. It's increasing quite steep, quite sharp gradient, meaning acceleration is quite high. After some time, a few seconds, 10-20 seconds, there will be some air resistance or drag acting on them. That means the resultant force goes down because there is going to be, the weight's the same, there's going to be a force acting in the other direction, so therefore the acceleration goes down. That doesn't mean they slow down, it just means that the gradient of the line becomes less steep as it starts to level off. After a period of time, let's say half a minute to a minute, the air resistance will equal the weight of the person. Because the forces are equal, more balanced, that means the person travels at a constant speed and be given by, on this velocity time graph, a straight horizontal line. And that's what happens when terminal velocity is reached, at constant speed. Now just know, exam questions do really like asking about this, but it won't always be skydivers. It could be a car driving along, where the car's driving force is counteracted by air resistance. It could be a cyclist, similar thing. It could be someone swimming in a swimming pool, where it would be drag acting the other way. They get a constant speed because of the drag acting opposite them is going to be equal to the driving force or the thrust they are applying. Now, talking about air resistance and frictional forces, on paper 2 you could also be asked about work done. Work done is given by force times by distance, so the work done overcoming frictional forces like air resistance would be given by that equation, and units of joules or Newton meters, because it's force newtons times by distance in meters. So if you've got a car traveling along or any vehicle, if it spots a hazard ahead of it, it's going to take a amount of distance to stop. Now hopefully it stops before that hazard, but we need to know what factors affect it. So stopping distance is made up of the thinking distance and the braking distance. Thinking distance, the factors that affect it would be things like drugs, alcohol, tiredness and distractions, and all things that would affect someone's reaction time. It's also affected by speed, because the faster you're going, the further you'll travel while you're reacting to the hazard. Braking distance is affected by road conditions, by weather, by conditions of the brakes, conditions of the tyres, and also speed, because the faster you're travelling, the further you're going to travel before you can stop safely. For thinking distance, we need to use the equation distance equals speed times time. The reason is because the velocity is constant, so therefore the distance is going to be proportional to the speed. And also the time, reaction time, is going to be proportional to the reaction distance, or the thinking distance. When we talk about braking distance, on the other hand, the distance is proportional to the speed squared. Because the speed is not constant, we can use the v squared equation from earlier. This means if I was to double the distance, then the speed is going to go up by a factor of 4. If I was to triple the distance, the speed would go up by a factor of 9. Going back to reaction time, exam questions love asking about this. You'd say, if you're asked about how does reaction time or how does something affect the stopping distance, you'd say reaction time increases, so therefore thinking distance increases. Please don't say things like the distance gets faster or slower, or the time gets faster or slower. That terminology only applies to things that have a speed. Time is indicated by it getting increasing or decreasing, so don't fall into that trap because it's not correct to say that. Reaction times are roughly about 0.2 to 0.9 seconds, and you can test this out by doing an experiment you might remember from biology, which is by holding up a ruler, having someone to catch it underneath, not giving them any warning, and then dropping it, and the further distance up the ruler, that's proportional to their reaction time. The next section is only if you are studying the higher tier or sitting the higher tier papers, but is on the combined science and separate science course, and I'm talking about momentum. So to calculate the momentum of an object, we use the letter P for it because M is already taken with mass. Momentum is given by mass times by velocity. Mass is in kilograms, velocity is in meters per second, so therefore momentum is given by kilogram meters per second, just by multiplying those units together. Momentum is always conserved in collisions, and we define the conservation of momentum as saying the momentum before equals the momentum after an event or a collision only in a closed system or if no external forces are acting. Just like with conservation of energy, it's a similar sort of idea. Now, much harder than quoting it is being able to apply it, and it's one of those things guarantee you'll forget to revise because it's quite a tricky thing. So let's first of all look at a bowling alley. Let's explain why a bowling ball slows down once it hits a bowling pin. So initially, so let's treat before and after, we would quote the conservation of momentum just to get a nice easy mark first of all, and we'd say that the ball initially has some momentum because it's travelling, it transfers some of its momentum to the bowling pin. Now the bowling pin isn't moving initially, but it then gains that momentum and it gains velocity because now it is moving. Because the momentum is being transferred, therefore as momentum is conserved, the bowling pin is increased in momentum, the bowling ball must have decreased in momentum. So therefore we'd say that the ball has decreased in momentum, so has got less velocity overall, or it says slowed down. Example 2, we're going to look at two trucks, one moving at velocity, one stationary, and this time they collide, but they stick together, unlike the bowling ball and the pin. So it says, explain what happens to the speed of the trucks. Now, as we just mentioned, the speed is going to go down, but we've got to be able to explain it. So momentum overall of this first truck is going to decrease, but momentum is conserved. So therefore we say trucks A's momentum is equal to the momentum of both trucks after they've collided and stuck together, so after the collision. The mass of the system afterwards, as both trucks are together, has increased because they're stuck together. So the mass of the two trucks together is greater, so the velocity must be lower to conserve momentum, as we know that momentum is equal to mass times velocity. So if one goes up, the other goes down because momentum can't change because it's conserved. Let's look at our final example, which is going to be about explosions. So this could be a cannon being fired, a gun being fired. It could also be someone stepping off a boat and the boat going the other direction. Lots of examples of this. We need to explain, for example, why a gun might have a lower recoil velocity than the velocity of the bullet. So what we've got to consider then is the momentum before anything is fired. So the gun's just by itself, sitting on a table or sitting in someone's hand. The momentum before must be 0. Now, as it's 0 before, it must be 0 afterwards, but we need to be able to understand why that's the case, because the bullet's moving and the gun's moving. The bullet's moving to the right, meaning it's got a mass times velocity right, and the gun's moving to the left. Because the velocity is a vector, so direction matters, we can consider one to be positive, the other to be negative because it goes the other direction. So we'd say something like, the momentum before is 0, the bullet's momentum to the right, which we say is positive, is balanced by the gun's momentum to the left. Now, because the bullet has a lower mass, that means its velocity must be higher, and the gun has a higher mass, so its velocity must be lower. So therefore that explains why the gun recoils but also has a lower velocity. If we were to consider before versus after, sometimes it's helpful to consider the mass times velocity of each. You can also just equal them to each other, because if you see in this equation here, I could just move that blue term to the left to be equal to the orange term. But if you're a separate physics student, you could be asked to calculate a number of things from situations like this. So I'm going to walk through those situations again, this time with numbers in them, and teach you how to calculate certain things. So in this first situation, let's do the speed of the ball. We're going to be asked to calculate the speed of the bowling ball, not just what happens to it. Now in general, for conservation of momentum questions, this equation I'm writing up here will guide you pretty well. It's not one in your equation sheet. Some people don't like using it. Sometimes it's useful, sometimes it might confuse people. But in general, it says that the mass of object 1 times by its initial velocity plus the mass of object 2 times by its initial velocity equals the same quantities, but with their final velocities. In this case, the speed of the ball is 5 meters per second and it's a mass of 3 kilograms. The velocity of the pin is nothing, so we can actually ignore that first term. So therefore, the total momentum before the impact is just 5 times 3, which gives me 15 kilogram meters per second. After the impact, both the ball and the pin are moving, so it makes it a bit trickier. So the pin, we know, has got a mass of 1 kilogram, as in the diagram. It's got a velocity of 10 meters per second, so therefore it's got a momentum of 10. The ball has got a mass of 3 kilograms, but we don't know its velocity, so we've got to work it out. So we've got the overall expression, momentum 15 equals 10 plus 3v. We don't know what v is. We can calculate v by subtracting 10 from the 15, which gives us 5, and dividing by 3 gives us the velocity as 1.666 or 1.67, rounding it to 3 significant figures. And this makes sense because we know the velocity of the ball must go down, but it's still going to be heading in the same direction. So it was 5, now it's 1.67. Let's have a look at example 2, which is calculating the speed of these trucks. So we're going to assign some numbers to them. Let's say the first truck is 100 kilograms, the second is 50, and the velocity of the truck going initially towards the other truck is going to be 50 kilograms. So the total momentum initially, just like with the bowling ball, is just the one object, but this time is 100 times 8, gives me 800 kilogram meters per second. After they've collided, we don't know their velocity, but we do know the momentum has to be the same, which is 800. So we've got the equation 800 equals the mass of the two trucks, m1 plus m2, multiplied by their velocity. Now we know their masses, so we can put the numbers in and say 800 equals 100 plus 50, 150, times by their velocity. And to find the velocity, I then divide the left-hand side by 150, which gives me 5.33 meters per second. Again, it makes sense. We're expecting the velocity to decrease from 8 meters per second, so it makes sense it being around about 5. Let's finally work out the velocity of the bullet if we know the velocity of the gun recoil and the masses of the two objects. So let's say the bullet is 50 grams and the gun is 400 grams and the recoil velocity of the gun is 3 meters per second. The bullet we don't know. So as you said earlier, the total momentum must be 0. So that means we've got 0.05, converting to kilograms, times by v. That's going to be added to the momentum going the other way, which is 0.4 grams times by minus 3. Don't forget it's minus because it's going in the opposite direction to indicate it's not going in the same direction as the bullet. If we simplify this down a little bit, we've got 0.05v added onto minus 1.2, and then we put the 1.2 onto the other side of the equation. So I've now got 1.2 equals 0.005v. Then we've got velocity equals that term 1.2 divided by 0.05, which equals 24 meters per second. The last thing we need to know if we're separate science students is impact forces. So how does momentum relate to forces acting in a collision, and how do we use that knowledge to keep people safe in things like car crashes? So let's say we've got a car that's going to hit a barrier. It can't be avoided. We can't talk about factors like in stopping distance. It's going to hit it. What safety features are there? So in a car, obviously, there are things like seatbelts. There are things like airbags, and also things like roll cages to help us out. There are also things like crumple zones in the car itself. Now, lots of these work in the same way. I'll explain how. So when you hit the steering wheel, if you're unfortunate enough to crash, if there's no airbag, you'll hit the steering wheel or the dashboard full in the face, and they're quite hard surfaces. That'll not be particularly pleasant. There'll be a high force. If you hit the airbag, though, what that does is it actually is able to sort of make the collision slightly different. So you could have a question about why do airbags reduce injuries, or it could be crash mats or anything at all really. It's all due to this equation here. So we can combine F equals ma with acceleration equals change in velocity over time to get the equation force equals the change in momentum divided by time. Don't forget momentum is m times by change in velocity. So using this equation, we can see that force is inversely proportional to time. So if I was to increase the time, the force decreases. So an airbag, for example, would increase the time taken for a collision. Because they're inversely proportional, the force would then decrease. So if I was to double the time taken, I would halve the force basically. And the final mark in a question like this would be as the rate of change of momentum decreases, that then causes this. So rate of change of momentum is just momentum, change of momentum divided by time. Don't forget rate just means divided by time. You could also say the acceleration decreases as well. This comes up a lot, and the other examples are crash mats, crumple zones, bending your knees when you land, trying to increase that time taken to mean the force is less. Waves look a bit like this, as we see on the left, and we can label a couple of key parts about them. So the first thing to label is the amplitude. That's the top of the wave, the peak to the middle or the equilibrium point. We would define it as the distance from a maximum displacement to equilibrium. Maximum displacement means just as high as the wave can go. The next thing we can define is our wavelength. Now, wavelength here I've labelled from one peak to another. It can be from any point in the wave to the same point on another wave. So here we could say it's the distance between two peaks on adjacent waves. Adjacent just means waves next to each other. And if we were to label the y-axis, we could label this with displacement being positive and negative about that equilibrium point 0. Another key definition to know with waves is what frequency means. So frequency is defined as the number of waves passing a point per second. You could also say the number of vibrations or oscillations per second. It's measured in hertz, which we abbreviate to Hz. Time period is another definition which we need to know. It's the time taken for one complete wave, and it's also commonly referred to as period instead of time period, and it's measured in seconds. Now, if I was to change my graph up here, the x-axis changing from distance to time, so we're looking at how the wave displacement varies over time. Now, what I had labelled as wavelength is now the time period. Because instead of the length of the wave, it's now the time taken for one complete wave on this graph. The relationship between frequency and time period is that frequency is equal to 1 divided by the period, which will be on your equation sheet for GCSE. Using these two diagrams I've drawn down here, a wave with a high frequency, i.e. lots of waves per second, if it's a sound wave, we describe it as a high pitch sound wave. That means the sound is a little bit higher compared to a low frequency wave, where the wave is a little bit lower, because there are less waves per second. Now, sticking with sound waves, if I was to, instead of changing the frequency or wavelength of the wave, if I was instead to change the amplitude, what we'd notice is that the volume of the wave will change. A higher amplitude wave, like the one here, would indicate a louder wave if we were to measure it on an oscilloscope or something like that, and a lower amplitude wave would indicate a quieter wave. So what this tells us is that amplitude, the more higher the amplitude, the more energy a wave has. In a sound wave, that corresponds to volume, but it could be brightness for light or anything like that, but a higher amplitude means more energy. If I was to multiply together the frequency of a wave and its wavelength, I would find the wave speed, or the speed of the wave, given by this equation here. This is obviously on your equation sheet, but you need to know the units. So frequency is in hertz, wavelength has to be in meters for this to work, and speed of anything we give in meters per second. Now, if you've noticed here, the units don't seem to quite make sense. That's because hertz is a bit of a special unit. Really, what we could say for frequency is measured in 1 divided by seconds, or 1 over seconds, because it's something happening per second. Next, we're going to look at transverse and longitudinal waves, the two categories of waves. So if I were to draw out a transverse wave, if I draw the oscillations going up and down, so the oscillations or the vibrations that cause the wave will still go left to right. So the direction of energy transfer is in a perpendicular direction to the oscillations. So we'd say a transverse wave, the oscillations are perpendicular to the direction of energy transfer. For a longitudinal wave, if I draw the oscillations as going left to right, the wave will still go in the left to right direction. So what we'd say is that the oscillations are parallel to the direction of energy transfer. You could also say the oscillations are in the same direction as the energy transfer of the wave. Now you notice here that the longitudinal wave looks quite different to a transverse wave. The particles themselves are more bunched up in some areas than others. Name we call the parts of waves that are bunched up are called compressions. Where the wave particles are spread out, or the air particles are spread out, are called rarefactions, not to be confused with refraction. Is a different thing. So in terms of examples of each, there are way more examples of transverse waves than longitudinal. Longitudinal, you're basically limiting yourself to sound waves, ultrasound waves, and P waves, which are a type of seismic waves, which we'll come on to later. Transverse waves are basically every part of the electromagnetic spectrum, so light, microwaves, X-rays, gamma rays, kind of the lot. Those are the main ones to remember there, plus ripples in water. One really important thing to note about waves is that waves are only ever passed on. So in the example of our hearing, let's say you were to hear a sound in the distance, a drum beating, it's caused by vibrations in the drum skin. That then causes the air particles close to it to vibrate, and their vibrations are passed on and on and on till they reach your ear, which then the vibrations cause your eardrum to vibrate, and then the message gets sent to your brain that you've detected a sound. Note, it's really important to note that the wave does not transfer matter. Waves only transfer energy. So in this case, the air itself isn't rushing into your ear, it's just the vibrations that get passed on. In the case of a transverse wave, if you've got a rubber duck or an animal sitting on the water floating, as the wave goes past, they only travel up and down, and the wave goes past them. They don't travel left to right in the direction of the wave. It's only the energy that's being passed on, not matter or not actual substances passed through the wave. Speaking of sound waves, you can measure the speed of sound in a slightly different way to we talked about earlier with the speed of waves in a string or in water. We can use the equation speed equals distance divided by time to work out the speed of sound. Now this is kind of tricky to do because to measure the distance you need really large distances, way over 100 meters, and to measure the time taken you need very good reaction times. So to do this yourself you need to measure a really large distance, and you need to bang a drum or some other object that's large enough for you to see the sound that's taking place, or see the banging of the drum that means the sound's taking place, and you time the difference in time between you seeing the sound and you hearing it. You might have noticed that with fireworks or other objects that are far away, you will always see the object first rather than the sound. So if you could time the difference between those two events, seeing and hearing it, and the distance between you and where the sound is coming from, you could work out the speed of sound. Now the speed of sound in air is roughly 330 meters per second. It will travel faster in a solid. That is because particles in a solid are closer together. The sound won't necessarily be clearer, but it will travel faster because there is less distance between the particles for the sound to travel in. When a wave hits a barrier between two different substances or two different media, the following can happen. The wave could be reflected, it could be absorbed, or it could be transmitted, or more likely a combination of any of these things. What happens when a wave gets reflected from a surface? So when light hits a mirror, we draw a ray diagram. The ray diagram must have arrows on it to show which direction the light or the wave is traveling in, and it must be in straight lines. So when the wave hits the mirror, we can draw on something called a normal, which is normally represented by a dotted line and is always at a 90-degree angle to the point where the wave hits the surface. So when the wave hits the mirror, we can label on something called the angle of incidence, represented by the letter I here. So when the ray comes out, the angle it makes with the normal, which is called the angle of reflection, is going to be exactly equal to the angle of incidence. If I was to introduce an observer, someone who could see the light coming from the mirror, to the observer or the person looking at it, it would look like the object is sort of behind the mirror. So if you trace the rays of light back from the person's eye past the mirror, it looks like the object is behind the mirror. So that means the object, the image, we say is virtual. It's not actually there. So reflection and what we're going to look at next, refraction, are examples for higher tier topics. Not separate science only, but topics you'd only find on a higher tier paper. So refraction is an example of what happens when a wave gets transmitted through a different material. Transmitted sort of means just let through. So what happens with refraction, let's go from air into glass this time rather than a mirror, is that the ray of light changes direction. Now we can draw the normal on here. This time the normal extends into the glass block, still at 90 degrees, and we can see that actually it bends towards the normal. So why does this happen? Well, to explain it, we've got to use something called wave fronts. So what I'm drawing here are perpendicular lines to the direction of the wave called wave fronts. Each one of them represents a peak of a wave. So if I've got a wave that's traveling from air into glass, I'm going to draw the wave fronts traveling along. Now hopefully we can see that because it's traveling at an angle, the wave would actually reach the glass at different times. Now when a wave hits a more dense medium, like for example going from air less dense to glass more dense, it's going to slow down. But if we look carefully, the side here on the left hand side of my drawing, the drawing of one side of the wavefront will slow down first, while on the other side that will not change initially, that will keep on going as it is. Then when we enter into the glass block, eventually the whole wave is now turned so that it's travelling a little bit more towards the normal. It's worth noting at this point that the diagram would not look the same if the wave wasn't travelling at an angle. If it was travelling perpendicularly to the surface, nothing would happen, it wouldn't change direction. It's all because it travels at an angle, one side of the wavefront hits the surface first. Now, if we were to measure the angles going into and out of the boundary, what we'd find is that from the angle of incidence, from the normal to the incident ray, that angle of incidence is going to be bigger than the angle of refraction. That's because the wave is travelling towards the normal. Another thing we can note from this diagram is what's happened to the wavelength. So the distance between the wavefronts represents the wavelength, and hopefully we can see from the diagram that inside the glass block the wavelength has decreased. Now, it's decreased because the speed has decreased. Those two things are going to be directly proportional. If we go back to our wave equation, speed equals frequency times wavelength, the frequency doesn't change. So if I decrease the wavelength, the wave decreases in direct proportion. This effect can also be seen in water. If you travel from deep water to shallow water, the same thing will happen. You'll find refraction occurs and the wavelength will change, again getting shorter in shallow water. The next section of the video is for only if you study separate science only. So we're going to look at ultrasound and also seismic waves. So ultrasound defines a wave that is a sound wave greater than 20,000 Hertz in frequency. This is outside the range of human hearing. Some animals can hear outside this range, but humans can't, so we call it ultrasound. Its most famous use is in fetal scanning, or scanning fetus while it's in someone's womb, but it can also be used to scan for cracks in materials in industry and also for cleaning things like dirt off watches. It's very similar to something called sonar, which it doesn't use ultrasound but uses sound waves to detect things like how deep a seabed is. I'm going to use this example to help explain ultrasound because it's easier to draw, but it works in the same way. So let's say I've got a ship on the surface of the water. It wants to find out what the depth of the seabed is to know where to place its anchor or when to go into port. So what it's going to do is it's going to emit a sound wave downwards, and the sound wave is going to reflect back up, or an echo. What the ship can do is it can measure the time taken for that sound to return to it, and it can use it to work out the distance, or in this case the depth. But because the time taken is the time taken for the sound to bounce back, that's actually going to be double what the depth is. So we would have to halve the time so we could find the accurate value for the depth. Now this works in the same principle when you're scanning a fetus inside the womb. The ultrasound will reflect back from a boundary between two different media, and then the time is measured, and then you use distance equals speed times by half of the time, and then the image is formed on a screen, doing this like sort of thousands of times per second to be able to form an accurate image. Lastly, for this little section, let's look at seismic waves. So seismic waves are waves caused by an earthquake or some sort of volcanic activity. There are two types of seismic waves. There are primary waves, or P waves, and there are secondary waves, or S waves. As the name suggests, primary waves arrive first, so they're faster. Secondary waves arrive second, so are slower. Now we need to know that primary waves are longitudinal waves, but secondary waves are transverse waves. Now because they're transverse and inside a solid, that means they do not travel through liquids. So S waves do not travel through liquids, really important fact to remember. When we're talking about earthquakes traveling through the Earth's core, P and S waves therefore travel in different ways. So if I've got my purple P waves here traveling through the Earth's core, they can sort of travel through any part. So on the other side of the world, you'll be able to detect P waves. They will refract slightly because they're going from one density of core to another, hence why they are sort of curving and changing direction here, but they'll still reach the other sides. In contrast, S waves we can only detect at certain areas in the Earth. When you don't detect S waves, you find something called a shadow zone because they do not travel through the core. So this means that because S waves don't travel through the core, we don't detect them. One conclusion, or the only conclusion we can draw, is that the Earth's core must have liquid parts to it, so S waves can't travel through it. So this allows us to find out what's inside the Earth without actually going there. So electromagnetic waves are made up of these 7 parts. We've got radio waves, microwaves, infrared, visible waves, ultraviolet, X-rays and gamma rays. Now hopefully it's obvious, but the only part we can see and directly detect as humans are visible rays. So we need to know what the order of these different waves are. A helpful way of remembering it, there are lots of different ways. My favourite is the one on the right hand side here, which is rabbits mate in very unusual expensive gardens. Your brain's more likely to remember a silly little scene, but anything you can do to remember the order of those 7 different parts of the spectrum would be perfect. Now, electromagnetic waves are made up of oscillating electric and magnetic fields. They all travel at the speed of light, or visible light, which is 300 million meters per second, or 3 times 10 to the power 8 meters per second. Obviously very, very fast. Now, all these different parts of the spectrum have different uses, which I'm going to list here. So radio waves are used for TV and radio. Microwaves are used for cooking food, obviously in a microwave oven. Both of them you can say they're used for communications. Infrared is used for thermal imaging, and electric heaters, or heating anything up like food using a barbecue or anything like that. Infrared radiation is basically just heat. Visible light is used obviously for seeing, but also for fiber optics, and also for things like CDs and DVDs. Ultraviolet is used for suntans in suntan beds or tanning beds, and also for energy efficient bulbs. X-rays are used for medical imaging, so to detect any broken bones. Gamma rays are also used for imaging, but also radiotherapy and sterilizing medical equipment. Well, one thing that's really useful to do for the sort of really high ability, high level questions is being able to link some of these uses to the properties of electromagnetic waves. Now, you can see I've written down here, I've got the right-hand side of my diagram where gamma rays lie. It's low wavelength and high frequency. It's all to do with these properties of the waves that makes them different and also makes them useful for different things. So, for example, if I'm going to use X-rays and gamma rays for medical imaging, they need to be able to go penetrate inside the body. Now, for example, gamma rays have a really small wavelength, which is smaller than the gap between cells and the atoms usually as well, so it allows them to penetrate inside the body. Some parts of the electromagnetic spectrum can be dangerous. It's only the ones that have a higher frequency than visible light that can be really dangerous. So that means there's ultraviolet, X-rays and gamma rays. They're dangerous because they are known as ionizing radiation. Ionizing radiation means if it gets into your body, it can mutate genes in cells, and it can also cause cancer. In particular, ultraviolet waves can cause skin cancer or can cause it to age prematurely, and gamma rays are the most dangerous in this regard because they are the most ionizing. Despite these types of radiation all being dangerous to an extent, they're useful to make things like X-rays. So if I was to compare the dose received by an X-ray, by a radiotherapy session, and by a sunbed session, we can analyse and compare the danger from their dose. So the dose we're using here, the units, is in millisieverts. So sieverts is the unit for dose, so you don't need to memorise it, but be familiar with it, and milli means 1,000th. So if I was to compare all these to the fatal dose, the dose needed to kill you, which is 5 sieverts, you can see that all of them, to different degrees, are far lower than the fatal dose. So we'd say that actually they're something to be aware of, but not dangerous, as they have a fairly low risk. But it is the reason why you can't have unlimited X-rays in 1 year, for example. Now, electromagnetic waves are all caused by changes in atoms. If you've watched my video about the Bohr model, we'll know that electrons exist in shells, but they can change between shells. When they drop from a higher energy shell to a lower energy shell, they emit electromagnetic radiation, or an EM wave. Gamma rays are emitted from changes in the nucleus, not in the shells of electrons. The last part of this topic on the electromagnetic spectrum is for higher tier students only, and it is a tricky one, but it comes up a lot in exam papers. A question might say, how are radio waves transmitted from a transmitter or received at a receiver? So from a transmitter, what happens, you have a metal which have 3 electrons. The electrons are caused to oscillate. When electrons oscillate at the right frequency, they produce a radio wave. So we say the alternating current in the transmitter causes radio waves to be emitted at the same frequency as the alternating current. Next, these radio waves make it over to our receiver, which looks very similar to our transmitter. This time, it's not the electrons that oscillate at the start, but it's the radio waves are absorbed. They cause the electrons to oscillate and therefore alternating current to be induced. So we say the radio waves are absorbed, they produce an alternating current at the same frequency as the radio waves. And that could be around 3 marks, so it's worth memorising that word for word, I would say. Let's talk next about light and colour, which is a topic you only need to know if you're doing separate science. This ranges all the way from red down to violet, via orange, yellow, green, blue and indigo. So the red end of the spectrum, the violet end of the spectrum, the violet end has the highest frequency but the lowest wavelength. Red end of the spectrum has the opposite. It has the lowest frequency, and that means it has the highest wavelength. One of the things light can do is reflect. So we're going to look at two different types of reflection. The first one is something off a flat surface, a very polished surface like a mirror. This would be called specular reflection, and that means the rays of light hitting the mirror parallel to each other also leave the mirror or surface parallel to each other, and that enables images to be formed. The other type of reflection is from a more rough surface. This is called diffuse reflection. So as you can see, the rays of light enter the mirror parallel to each other, but they exit at different angles because the surface is rough. It does not reflect them evenly, so they end up being scattered. So this would be any rough surface that's not a polished mirror, so clothes, carpet, walls, anything like that. So if I have white light, which if we don't know, it contains all colours, if that hits the surface, and if only the red part of the spectrum is reflected, with orange, yellow, green, blue, indigo, violet being absorbed, that shows us that the colour is red. So the colour of the object is red. And if I was looking at that object, you would see it as red because it's only reflecting red light. In another example, we've got white light incident on this surface down here. Let's say we've got red being reflected and all the blue parts of the spectrum being reflected, so blue, indigo and violet, but orange, yellow and green absorbed. So what that would mean is that would combine the reds and the blue colours together, so the object would be purple, as it's reflecting both red and blue light, so they combine together in this case to make purple. If we have no light being reflected, so in this example here all the white or any colour is absorbed, that shows us the object is black or appears black because there's no light reflected and all colour is absorbed. If there's a red surface with blue light incident on it, it's not going to reflect any light. Red surfaces only reflect red light, so if there's no red light incident on it, it cannot reflect it. So therefore no light's going to come off it. If you were viewing it from afar, you would say it appears black because it's not reflecting any light. Next, let's talk about filters. So filters don't allow light to be reflected, they allow light to be transmitted. So let's have white light going through a red filter. Now a red filter will transmit red colours, but it will absorb all other colour wavelengths. So that means in this case that the red light goes through, but all the other colours are absorbed. If we were then to put this red light through a blue filters do the same thing, but they only transmit blue, and they'll absorb all the other colours. So because it's not white light hitting this filter, it's only red, that means that it's going to absorb the red, but there's no blue light for it to transmit. So therefore it's not transmitting any colours at all, it's absorbing all the light that's incident on it because it's just red. Next we're going to look at lenses. So there are two types of lenses you need to know. There are convex lenses and there are concave lenses. Now the way to remember it is concave is sort of bends inwards at the middle, looks a bit like a cave, whereas convex is the other one. You also need to be familiar with the symbols for each, which I've drawn here. So convex has another name. Convex, the other name for it is a converging lens. As you can see the rays of light here, they enter the lens parallel to each other, but they converge to a point or a focal point. Concave lenses are known as, on the other hand, diverging lenses. That's because the rays of light that enter parallel to each other will diverge or get further apart from each other. So we need to be able to draw lens ray diagrams. I'm going to set up a focal point on each side of the lens. This will normally be done in an exam question for you. The distance between the focal point and the lens is known as the focal length. So I'm going to represent my object as an arrow. It could be anything, it could be a tree, it could be a person, but an arrow is simplest to draw. So the first ray of light we draw, both of them are going to come from the top of the object. The first ray of light is going to go horizontally from the top of the object through the lens, then it's going to refract and it's going to go through the focal point on the other side. The other ray of light we're going to draw is going to go through the center of the lens, and this one isn't going to change. So the image gets formed where the rays of light cross over. So in this case, as we can see, if I'm drawing the image in here, it's actually upside down. The top of the image has to still be where the rays of light cross over, because that's where they've come from. So we describe this image in three ways. The first way is to say it's inverted, meaning it's upside down. It's also a little bit magnified, not too much in this diagram, but it's got a little bit bigger, and it's a real image. Real image means the rays of light cross over after a lens or a mirror, and they can be projected onto a screen. If I was to put a screen there, then this would be what's formed. An example of this would be like a cinema screen when you're projecting something from a projector. The next example we're going to look at is a convex lens, but the object is much closer. Let's draw my rays of light in. My first ray is going to go parallel to the axis, horizontally, through the lens and then through the focal point. My next ray goes through the center of the lens, just like before. But we notice something weird happens. The rays of light are not going to cross over on the right-hand side of the lens. So therefore, we can't have a real image being formed. So therefore, we have to trace the rays of light back so we can find a virtual image. So if I trace these two rays of light back, they go quite far back and the image ends up being quite large because the rays of light have been traced back so far that the image has got a lot bigger. So we describe this image as upright because it's not upside down, it's magnified, it's a lot bigger, and it's virtual, meaning the rays haven't crossed over so it can't be projected onto a screen. And to calculate magnification, we need to know the object height and the image height, just like you would need to know in biology. The last lens we're going to look at is our concave lens. It doesn't matter where the object is for this, all the diagrams look the same. So I'm going to have my ray of light going first of all from the top of the object horizontally to the lens, but this time it's not a converging lens, so the ray of light doesn't go down through the focal point, it's actually going to converge away from the other rays of light. But I've got to be careful how I do this. I draw it going away from the rays of light, but it's got to be in line with the focal point on the left-hand side of the lens. So I'd say it's horizontal to the lens, but you sort of trace it back through F. I would do a dotted line to indicate it's not a real line, it's not a real ray of light. The second rule is unchanged. That still goes one ray of light through the center of the lens, through the center of everything. Now hopefully we should note that the two rays of light don't cross over on the right hand side of the image. There's no real image formed, but they do cross over with one of the virtual rays, or the rays I've traced back. Now this image is therefore upright, it's diminished, meaning it's quite significantly smaller, and it's a virtual image. Next we're going to talk about blackbody radiation, which again is only for separate science students. So let's say we've got a cup or a mug of water, for example, and I've got a heater. So if I was to provide it with some heat or some infrared radiation in, and it's going to re-emit some of that back into the surroundings. Now, if there is more infrared radiation in than there is coming out, that means the temperature of the mug or of the liquid will increase. If I was to reverse it and there's more infrared or heat coming out than going in, the temperature would decrease. And if they are equal to each other, the temperature will stay constant. Now, this can be applied to things like planet Earth. So for the Earth's temperature to increase, and this is how basically the basics of how global warming works, there must be more radiation being absorbed than there is emitted. And instead of saying radiation or waves come in and go out, we should be using those key terms. They're really important. So for example, for my cup of water or tea earlier, we'll say radiation absorbed and radiation emitted instead of in and out. Now, we need to know what this thing called a blackbody is before we can understand blackbody radiation. So a perfect blackbody is defined by something that absorbs 100% of the electromagnetic radiation incident on it, or that is going into it. It also emits or re-emits 100% of that electromagnetic radiation, hence why it's known as a perfect blackbody. The last thing for this topic is to look at how the intensity of the EM radiation emitted varies depending on the temperature. So generally speaking, over all the different wavelengths, you're going to have a higher intensity for hotter materials versus those for colder. They're all going to emit radiation, but at different intensities and different wavelengths. So we say that different temperatures will emit electromagnetic radiation at different wavelengths and different intensities. For example, the peak of this hotter emitter might be in the UV range, whereas in the colder might be in the visible light range, just like you'd find for different temperatures of Bunsen burner, the different wavelengths are emitted. The hotter one emits blue light, the colder one emits more sort of orangey red light. Questions on electromagnetism are usually some of the worst answered at GCSE. So in this video, I'm going to break the topic down stage by stage so that you have a really good understanding what the topic is and how to answer any question on anything to do with electromagnetism. So first of all, what is magnetism? It's an example of a non-contact force. That means that two magnets or magnetic material do not need to be in contact or touching each other for a force to be exerted. There are two situations and two types of forces you can have with magnetism. You can have opposite poles and you can have like poles. Opposite poles will attract each other, like poles will repel. The magnetic field around a bar magnet looks a bit like this. We have loops of magnetic field lines pointing from north to south. In an exam, you'd only be required to draw a couple of ones on each side, so please do not draw loads and loads. So how do we know that magnetic fields look like this? We cannot see them with the naked eye, but we can use a couple of different demonstrations to show them. We can use iron filings and sprinkle them on some paper on top of a magnet to show the general shape of the field. We can also use a plotting compass, that's the kind of compass you use for navigation, to show the shape but also the direction of the field. So how we do that is we place the compass at different points around the magnet. When we do that, the needle will change direction and it points in the direction of the magnetic field, which is towards the South Pole. Plotting compasses will normally point following the Earth's magnetic field. That's because the Earth has a magnetic field inside it, which actually has a South Pole near the North Pole. So magnets will point towards the geographical North Pole, because actually that's a South Pole inside the Earth. And the reason the Earth has a magnetic field is because it contains a lot of iron in it. And it actually flips every sort of 100,000 years or so, but the minute it's got a South Pole near the North Pole. Okay, so those types of magnets, like bar magnets, are usually known as permanent magnets. Next, we're going to look at the type of temporary magnet called an induced magnet or induced magnetism. So induced magnetism can be defined as when a material becomes a magnet when placed in a magnetic field. So let's look at an example of this. Now this only works with magnetic materials such as iron, we've already discussed, and we've also got steel, cobalt and nickel are the 4 magnetic materials you need to know about for GCSE. So with any of these materials, let's say it had a bunch of iron nails or paper clips on the ground, not close to the magnet. When I bring them close to the magnet, the reason they get attracted to the magnet is because they temporarily become a magnet themselves. So they'll have a north and a south pole on them designed to be attractive to the magnet that is attracting them. And if I was to add more on the end, they would also become little magnets as well. And it's only ever attractive, not repulsive. A magnetic field is defined as a region or area around a magnet where a force acts on either another magnet or a magnetic material. That's how you define it in words. The magnetic field is strongest at the poles. Both poles are equally strong, and it decreases the further away you get from the magnet. Let's next talk about how magnetic fields are produced by electric currents. Now, when you have a current flowing through a conductor or a wire, the electrons themselves cause a small magnetic field to be produced around the wire. So the fields are circular, and we can figure out their direction by using something called the right hand grip rule, which is based on your right hand. If you stick your hand with sort of thumbs up, the thumb will point in the direction of the current, your fingers will point in the direction of the magnetic field in sort of a circular motion around the wire. So in this case, the current's pointing sort of up and right, the magnetic field is sort of coming around in this direction, indicated by the arrows on the magnetic field in the diagram. If I was to make the magnetic field around a wire stronger, I could coil it into what's called a solenoid. A solenoid is just a coil of wire with current flowing through it, and it is able to increase the magnetic field strength from just the straight wire earlier. Now, the magnetic field around a solenoid, as I'm drawing here, is very similar to that around a bar magnet. It's very strong and uniform in the center of the coil, and we can figure out the north or south pole by looking at either end. Now, you can only really use your imagination with this one here. If you looked at either end of the coil, the current would either be going clockwise or anti-clockwise. And the way to remember it is by remembering these little diagrams. If I wanted to make the magnetic field even stronger, I can make it an electromagnet by adding an iron core. The advantage of an electromagnet is that it can be turned on and off very easily, and I can vary the strength by varying the number of turns on the coil and also the current flowing through it, same as for a solenoid. There are lots of uses for electromagnets, things like circuit breakers in household appliances, relay circuits like a starter motor on a car, electric bells, electric locks, and lots of other examples as you see on the screen. The next part of the video is only suitable for higher tier students. We're going to talk about motors and the motor effect. So when you place a conductor, like this wire here, in a magnetic field, the two magnetic fields will interact. Now, do you remember before we talked about the wire having a magnetic field around it? Well, between the north and the south pole, there's another magnetic field, and when the two fields interact, they exert a force on each other. That's what's known as the motor effect. Now, Fleming's left-hand rule can tell us the direction of the force. So using this image here, I'm not going to try and draw this out myself, but using the image here, we can see that the thumb's direction is going to tell us the direction of the force or motion. The first finger tells us the direction of the field, so north to south, and the second finger or the middle finger tells us the direction of the current. So in this case, for my example, I've got the field going left to right, so I point my first finger that way. The current is going sort of away from me, so I've got to twist my hand so it's going in the opposite direction to where it was before. When I do that, my thumb is pointing in the downwards direction, so therefore the force goes down. Factors affecting the size of the force in the motor effect are as follows. They're affected by the current flowing, by the length of the wire, and something called the magnetic flux density, which is essentially the same thing as magnetic field strength. If I was to reverse any of these factors, the force would also reverse. Now, the equation that governs the motor effect encompasses all these factors. So if the force is equal to B times by I times by L. Now we should know F force is measured in newtons, I current is measured in amps, length we have to have in meters for this to work. The new one is B. B is the symbol we use for magnetic flux density, and it's measured in Tesla or capital T. Useful to note is that Tesla is normally quite a small unit. Normally you'll find milliteslas or 0.01 teslas. It's not normally hundreds of teslas. That would be a very, very strong magnetic field. Now the motor effect seems like not that useful. What's the point in making a wire jump up or down? Well, the point is we can actually make things go in circles and things like you'd find in electric cars, in an electric drill, in a hairdryer, a washing machine, anything that relies on electricity to go around in a circle. So an actual motor would look a bit like this. So you'd have a piece of wire, but instead of it being a straight piece of wire, it would actually be a coil. The reason it's got to be a coil is because we need current flowing in different directions depending on where you are in the coil. So if I connect this to my cell or my power supply, on the right hand side I've got the current flowing in the same direction as my example just now. So using Fleming's left hand rule again, I can figure out the force is going to be acting downwards. On the other side of the coil, however, the current is flowing in the opposite direction. It's now flowing towards me. So in that case, what I can figure out is that the force is going to go the other direction. So on the left-hand side it's going up, the right-hand side it's going down. This causes the coil to rotate. And if you ask the question about it, you'd say the coil is rotating. You'd say current is flowing in opposite directions on each side of the coil, so the force is in opposite directions. And you probably want to explain the motor effect as well, and depending on how many marks the question's worth. Now, some of you might be able to notice there's a problem with this. At the minute, if this coil was to rotate, it would just rotate half a turn and then go back. That's why we need something called a split ring commutator to help us. The split ring commutator reverses the current every half turn, so it allows the coil to turn continuously. So what it does is a rotating sort of circle with a gap in it, where it flips over positive to negative every half turn, so that the coil would experience the force on opposite directions on each side of the coil. An application of this you need to know if you're studying separate science is in a loudspeaker. So any speaker in the world works like this. So I've got an image on the screen now. It relies on alternating current, which is changing direction, to cause a motor effect in the coil. Because it's alternating current, it's changing direction, so the coil vibrates, it changes direction quickly. Therefore the cone, where the sound comes out from, also vibrates. Air particles that are near the cone will vibrate at that same frequency, which means sound waves at the same frequency which the coil is vibrating at. Next, let's talk about the generator effect, which is something that again is on the separate science only syllabus for physics. So when a conductor moves in a magnetic field or relative to a magnetic field, we get a potential difference being induced. Now this looks similar to the motor effect, but in reverse. Instead of producing movement, I'm putting movement in and I'm getting electric current or potential difference come out the other end. Now it's important to note we only get current induced if the conductor is part of a complete circuit. That's because current is rate of flow of electrons, and the electrons can only flow if there's a complete circuit. Now this can also occur if you've got a magnetic field moving relative to a conductor. Like a magnet being pushed into a coil of wire, the same thing would happen. If you don't have movement of the wire, then you won't get any current being induced. If you only have movement in one direction, then you get current flowing one way, and if you change the movement of the wire to go the other way, the current will flow in the opposite direction, usually indicated by an ammeter reading going the opposite way or turning negative. Factors affecting the potential difference or the current induced would be the speed of the movement, so if you move it faster, you'll get a higher current or PD, the magnetic field strength, the strength of the magnets, or the number of turns on the wire, which we'll come on to later. If I've got a coil of wire, more turns means a higher potential difference induced. Now, one very important thing to note, which is a very small part of the AQA specification, is that for any induced current, actually, when we induce a current, we have these tiny magnetic fields around the wire, as we covered with the motor effect. When we have these tiny magnetic fields around the wire, they're also going to oppose the motion that caused them. Where would you know where to spot this? You might have questions about something being harder to move, or it sort of slows down, some sort of resistance to this motion, and this is why. Now, in general, looking at the motor and the generator effect, how would we know the difference between them? In a motor, you supply current in a conductor and a magnetic field, you get force or motion out. Generators, you supply force or motion in, and you get current out. So we'll talk about generators then. Generators involve a coil of wire, so you've got current able to flow in both directions. There are two types of generator, and they're both caused by something being rotated and then a PD being induced and measured by a voltmeter, for example. In an alternator, as the name suggests, we're going to get alternating potential difference out. So we get potential difference flowing one way, then another way, then another way, meaning we get alternating PD. For a dynamo, we have this thing called a split ring commutator, which we looked at when we looked at the motor effect. This reverses the current every half turn so that the current is always direct, or the potential difference is always direct. So if I was to draw a PD time graph of this, it's not going to be flat, but it's going to be not negative. So every time that the generator would be negative, the PD would be negative, it gets reversed. So now it has this sort of shape, as you can see in the diagram. That's for a dynamo. Clue of the name is that a dynamo begins with a D, therefore it's going to produce direct PD. Alternator is alternating PD. One big example of this is going to be, rather than power stations and things like that, is a microphone. Now, a microphone works in the opposite way to a loudspeaker. So sound waves cause the diaphragm to vibrate, and the generator effect is going to happen because the coil is vibrating. That means there's going to be alternating PD induced because it's changing direction, which then gets sent to the circuit. So a microphone, instead of a loudspeaker going current to sound, this is going to go sound waves to current. Transformers are part of the national grid, and you can have either step up or step down transformers. Step up transformers will increase the potential difference to reduce heat loss. We'll come on to that later. Step down will decrease the potential difference to make it safe to use in homes. Transformers look a bit like this. You've got a giant square iron core with coils of wire wrapped around each side. These are known as the primary coil and the secondary coil. Now, on the primary coil, you supply an alternating current to the coil. And what that does, as we looked at with electromagnets, you produce a magnetic field. Because it's alternating, you have a changing magnetic field produced around the primary coil. Now what this field does is, because it's close enough to the secondary coil, that allows an alternating potential difference to be induced across the secondary coil. Without touching it, the current doesn't flow through the core, but it happens due to the generator effect, which we looked at before, which is when you have a changing magnetic field around a conductor, you induce a potential difference. So if there's an ammeter at the other end, we can talk about there's an alternating current being induced as well. Now, as in the diagram, the number of coils on the primary versus the secondary coil can be different, or will be different, depending on whether it's a step-up or a step-down transformer. So in this case, it's a step-down transformer, indicated by the fact that I've got less coils on the secondary coil than the primary coil. The equation that governs the number of turns on the coil versus the potential difference is here. So it says that the ratio of the number of turns on the primary over the number of turns on the secondary coil is equal to the ratio of potential difference supplied to the primary coil and the secondary coil. So if I give my example here, my ratio is it goes a step down transformer because there's less turns, it goes down by a factor of 3/2, so therefore the potential difference would have to go down by a factor of 3/2 as well. Last equation to do with transformers is one that assumes that they are 100% efficient, which they're not, but allows us to use this equation as an assumption. So if something's 100% efficient, it means that the amount of energy that goes into it is equal to the amount of energy that comes out, or the power in is equal to the power out. That's the energy per second. Now, power, we might know from paper 1, the electricity topic, is given by current times by potential difference. So that means across the primary coil, the current times the potential difference is equal to the power across the secondary coil, meaning the current times potential difference across the secondary coil, indicated by the letter S and letter P for primary coil. So when we increase the potential difference for a step-up transformer, what we're doing is doing that to reduce the current. So if I increase the PD, the current has to go down to keep the power constant, and that reduces heat loss to the circuit. We are talking about my all-time favourite GCSE topic, space. Let's have a look at the planets. Now, we don't include Pluto, sad face, because it is now classed as a dwarf planet. There are lots of others like it. We just happened to be discovered in the earlier 20th century. And some of them have their own moons. We call them natural satellites. Jupiter and Saturn have absolutely loads between them. We keep finding more. It's probably going to reach 100 soon. Part one of this video, we are going to talk about stars. We're going to look at how they're born, how they live, and how they die. So first of all stars start off and they form as a nebula, which is a fancy name for a cloud of dust and gas, bits of atoms that are left over from other solar systems usually. Now that when they come together will form a protostar. Then after a protostar has existed for a period of time, it becomes a main sequence star. And the main sequence star, like our sun, can go one of two ways, depending on if it is a heavy, high mass star, or if it is a low mass or average star. So let's do our sun first of all. So the low to average mass, after it's been a main sequence star, will become a red giant star. Then it will become a white dwarf star, and after all the radiation is emitted from a white dwarf, it becomes a black dwarf. Now for high mass stars, it's slightly different. Instead of a giant, they are a red supergiant star. And after that stage, you have what's called a supernova. After that stage, you go into two different sections called either a black hole or it forms a neutron star. So a nebula or cloud of dust and gas is pulled together by gravity. Even though dust and gas doesn't have much gravity, enough of it gets pulled together over millions of years. Next, when we have our protostar forming, the protostar is kind of like the stage before the star, and this is when if pressure and temperature is high enough for nuclear fusion to occur or to begin. But essentially, nuclear fusion is when two light nuclei, usually hydrogen, combine together to make helium, and it releases energy. But this only happens at high temperatures and pressures, so you need a lot of the matter in one place under high gravity for this to begin. Next stage, main sequence star. This comes up a lot of times in exams. This is the stage our sun is in currently. It's been there for about 5 billion years, and it will continue to be there for about another 5 billion years or so. So let's look at what it's like. Now, it's a very stable phase. Stable meaning the forces acting on it are balanced or in equilibrium. So the forces that are going inwards are gravity pulling everything inwards. The forces outwards are a bit trickier to describe, but they are caused by the thing we just talked about, nuclear fusion. Nuclear fusion releasing energy, and you'd say a phrase like pressure from nuclear fusion. Now, if those forces are equal or balanced, then the star stays the same. Basically, that's why our sun doesn't change day on day. It doesn't get bigger or smaller. Now, once that stage is finished, we are going to talk about what happens when it goes to the red giant or red supergiant phase. So the red giant, first of all, once the hydrogen runs out, then it is no longer a main sequence star. What will start happening is it starts to fuse heavier and heavier elements. So instead of hydrogen, it might be helium and helium. Then it might be carbon, it might be oxygen. These heavier elements mean that it expands into a red giant, and it has a different color. In the red supergiant phase, this happens to elements all the way up to iron. After this point, all fusion will stop at a certain point for a low to average mass star. And at that point it shrinks back down, becomes a white dwarf, then even that radiation ceases, it becomes a black dwarf. Now for a supernova, all fusion stops once it gets to iron, but the result is a bit more spectacular. So in a supernova, let's think of all the forces acting on a star. If fusion stops, then there's no outward force, so there's just gravity acting. So if there's just gravity acting inwards, what will happen is the star will all of a sudden kind of start to shrink. It will start to get smaller until it gets to a core, really dense core of iron. Then it will suddenly kind of rebound and expand outwards, and that's the supernova, an explosion of a star, all expanding outwards, throwing all the elements inside it all across the universe. Now, these elements are heavy elements, not just all the way up to iron, but you can have heavier ones than iron. What gets formed at the end is a black hole, which is a very, very dense object, or a neutron star. Redshift is an example of something called the Doppler effect. Now, the Doppler effect doesn't apply to stars or space necessarily, but it can apply to any wave. So let's look at an example. So let's say you're standing in a street and you hear an ambulance drive past you. Now, the ambulance is obviously got its sirens on, it's on its way to emergency, it's emitting sound quite loudly. So you, as you hear the ambulance go away from you, will have a different perception of the sound to someone on the other side of the ambulance. So let's say the sound waves hit you as it goes past you. Someone on the other side of the ambulance, which is travelling towards them, the waves are slightly closer together because the ambulance is travelling towards them. Now, as you can see from the diagram, if you compare the wavelengths, if it's travelling away from you, there's a longer wavelength. If it's travelling towards you, it's a shorter wavelength. For sound, a longer wavelength sound means that it is a lower pitch or a lower frequency sound, and a shorter wavelength means there's a higher pitch or a higher frequency sound. Now, with redshift, we apply this to distant objects in space. So let's take our two people again. Let's say they're in different parts of the universe, and we've got a galaxy that's emitting a light. If it's traveling away from us, it will have, like we talked about, a longer wavelength. So let's look at the colors of the rainbow and see which one's got a longer wavelength. So red, orange, yellow, green, blue, indigo, violet. Hopefully you can see from the diagram that violet and blue has a shorter wavelength and red has a longer wavelength. So as the galaxy travels away from the person or the observer, the wavelength it is giving off is slightly shifted towards the red end of the spectrum, or a longer wavelength. And if it's traveling towards you, it's what's called blue shifted, which means the wavelength has been decreased, so it is more blue shifted. How you describe it in an exam is redshift is when light emitting from that are moving away from Earth has a shifted towards the red end of the spectrum. Now, you could say it's got a longer wavelength here as well. That would be also some extra information to put in, but please don't say it's more red. That doesn't get you marks. It's shifted towards the red end of the spectrum. Now, if we want to talk about something that's blue shifted, obviously you replace red with blue, and that would be something that's moving towards the Earth, and it'd be shifted towards the blue end of the spectrum. Now, we don't talk about blue shift as much because almost all of the galaxies we observe in the night sky, apart from our nearest neighbour, is red shifted. So what that means is if we were to observe all the different colours in a spectrum, don't worry too much about what a spectrum is, we learned a little about it at A level, but it shows all the different colours, and there are what's called absorption lines. And if these lines have shifted slightly towards the red end, like these ones have, then that shows us that the light from that galaxy is red shifted and it's travelling far, it's moving further away from us. So what do we notice when we look at all these things? Well, we actually notice that almost all those galaxies are redshifted. So actually almost all those galaxies we observe are moving further away from us on planet Earth. So let's look at then if we were to plot a graph of these two things, and this is something that Edwin Hubble did over 100 years ago now, which is to look at the velocity versus the distance they are away from us. So the further away they are they moving faster or slower? Well, actually, if you plotted all the points, there's a fairly positive correlation, and the two things are actually directly proportional because it's a straight line and it goes through the origin. So what that shows us is the further away a galaxy is, the faster it's travelling. So the further distance, the higher the velocity, and that means that it all came from one point, which is the Big Bang. Let's have a look at evidence 2, CMBR, which stands for Cosmic Microwave Background Radiation. Now let me tell you about a little bit how it works. So the analogy I'm going to use is that of a balloon. So a balloon is like space, it's expanding. So if I was to draw a little dot on the balloon or a symbol, if I was to then blow up the balloon, the dot stays the same, but it kind of expands. This is representing space expanding. Now, Cosmic microwave background radiation. Radiation is a wave, so if I was to draw a little wave on the balloon, it would expand out to be an even bigger wave with a bigger wavelength. So how we'd go about describing the CMBR is to say that radiation, this is from a long time ago, this is from the Big Bang itself, or the very short seconds after the Big Bang, wavelength has increased because, or as, the universe has expanded, so has expanded outwards, and this is a big deal because it actually was predicted before it was discovered. So this is a massive evidence for the Big Bang being true, is that this radiation has expanded to the microwave region of space. Now, if you were in school in a few billion years' time, if you look at the EM spectrum, currently it's microwave. If it was to expand even more, have a higher wavelength, it would actually become radio waves. But don't worry, it'd be quite a few billion years before that happens. And there we have it, the whole of paper 2 in just under 1.5 hours. Well done for making it to the end. Please leave the video a like if you enjoyed it, and also check out my channel for other videos on things like required practicals, exam questions that come up a lot, and different exam technique tips to help you out with GCSE Physics Paper 2.